to start discussing sound waves, and before we do that, I would like to quickly review elastic properties of materials. So, we can cause three types of deformations on materials. The first one is the scenario here. You have a bar that is attached to a table. On one end, we're applying a force. The force is acting on a perpendicular um, area A here, this area A, and therefore there is a force per area, there is a pressure. And as a result of pressure, what is the response of this material? It's going to be a change in its length. So there will be an increase in the length by an amount delta L. And if we haven't exceeded the elastic limit, when the force is removed, the material will go back to its original length. If the force is too much, then the effect is irreversible and it's going to cause a plastic deformation. Now, within the elastic limit, the force that we're applying per unit area, force per area, is called stress. Force per area, we show it with sigma, it's called stress. And the result of applying this force is a change in its length. The change in the length, delta L, divided by the initial length, we call epsilon strain. And stress and strain are related by Young's modulus. So sigma is equal to Young's modulus times epsilon. So stress and strain have a linear relationship, and Young's modulus Y is a material constant, material dependent constant. Now, if we move to a different scenario where we apply the force parallel to one of the faces of the material, as you can see here, if the force is applied in couples on the top and the bottom planes of the material, for example, you have a book, you're applying a force on the top to the right, and the static friction is going to act to oppose the force that you're applying. It will be to the left, and at the end, what happens is we're going to get deformation such that the top plane will move with respect to the bottom plane. And now we have the force that we're applying per area A, but this area is the area of the plane. It's not the perpendicular area. So in order to distinguish these two, maybe we should put a perpendicular here. This is the parallel area. And as a result of this force, we're getting a stress sigma, that's shear stress. And the end result of this stress is a change in the position of the top plane with respect to the bottom plane. The motion is by an amount delta x. So the ratio delta x divided by the distance between the two planes, delta x over h, is epsilon, the shear strain. And we find that the shear stress is equal to shear strain times the shear modulus. Okay. And shear modulus is also a material constant. Now, the first scenario is where we have an object on which we're changing the pressure. For example, we take this from 1 atmospheric pressure to 2 atmospheric pressure, etc. So the force per area that we're applying on all sides, so this is area A, is increasing. So So we have a change in pressure, delta P, because we have a change in the force that we're applying per perpendicular area. And what is the response of the material? The volume changes. So there will be a volume change, delta V over V initial. So this is going to be related to the change in pressure, such that we have to consider that the increase in pressure causes a decrease in volume, so that we will have the change in pressure is equal to minus Bulk modulus times the change in volume divided by initial volume. We need the minus sign because the bulk modulus is defined as a positive quantity, so delta V is negative, bulk modulus E is positive. Again, bulk modulus E is a material quantity. So we have, for one-dimensional deformation, Young's modulus, stress force per perpendicular area is Young's modulus times strain, change in length divided by the initial length. Then we have shearing when we apply a force couple on the top and bottom planes of a material. Force per area of the plane that we're applying is shear stress. The shear strain is the change in the relative position of the plane, so by amount delta x divided by the distance between planes, and those are related by the shear modulus. And if we change the pressure that we're applying on the material by increasing the force on the material, the end result is a decrease in volume, delta V over V initial times bulk modulus, the minus sign is equal to the change in pressure, because delta V is negative, bulk modulus is defined as a positive quantity. Okay, after this review of elastic properties of materials, let's move on to sound waves. So sound waves, you can think about longitudinal waves of pressure and density. So the first thing is that they are longitudinal. That's my first point. Longitudinal pressure and density waves. And how do we create sound waves? One way to do that is to take a gas tube and have a piston on one end. So you can see that before the piston moves, the gas is undisturbed, and we compress the gas by moving the piston to the right by some amount, and then when the piston stops, the compressed pulse continues through the gas with what speed? The speed of sound. And when we pull the piston back to its original position, we have this series of compressions and rarefactions propagating inside the gas. So we can move the piston in simple harmonic motion back and forth and create these variations in pressure and density. And you can see here between two maxima in pressures, you're going to have one wavelength. So you're going to have a longitudinal wave. The gas elements are moving back and forth parallel to the propagation velocity of the wave. So they're longitudinal waves. Okay, so we can create it, can be created by moving a piston at one end of a gas tube in simple harmonic motion. So when you have compressed gas, that means we have high pressure, high density, and therefore We call this the compression part of the cycle. And when we have a pullback, then we have low pressure and low density, and we call that rarefaction. So compressions and rarefactions are moving, alternating compressions and rarefactions are moving at the speed of sound. So sound wave basically is alternating compressions and rarefactions move with the speed of sound inside this gas. And since any small element of the gas moves in simple harmonic motion parallel to the direction of the wave, we have a longitudinal wave, we can talk about displacement of gas elements. So displacement of gas elements are moving such that we can talk about this wave function S as a function of x and t, where x is this axis on which the gas is propagating. We have a maximum displacement S max multiplied by cosine kx minus omega t, where S max is my displacement amplitude. Displacement amplitude. And so this is one way to describe the sound wave. It's a displacement by using the displacement of the gas elements. And corresponding to this displacement of the gas elements, similarly, we have the pressure, the gas pressure changes such that the change in pressure is a maximum change in pressure, delta P max, times sine of kx minus omega t. So you notice that one is a sine, the other one is a cosine, and we're going to see why that is in a moment. All right, so we can describe the sound wave equivalently by looking at the displacement of the gas molecules. Then it's going to be a maximum displacement times cosine kx minus omega t, or by looking at the change in pressure, the pressure wave propagates such that delta P is delta P max sine kx minus omega t. So they seem to be out of phase. Now, let's take a small cylindrical element of undisturbed gas. It has a length delta x and area A. When I move the piston on one end to compress this gas, I see that a portion of the gas moves to the right hand side. So for this gas element, there's going to be a change in the volume. So I have a small cylindrical gas element which has an initial volume, its area A multiplied by its length delta x, and when I compress it by moving my piston to the right, it's going to have a final volume A times delta x has decreased by an amount S1, and then I have additional length on the right hand side S2, so it's going to be A delta x plus A times S2 minus S1. So I see that I have a change in volume V final minus V initial is equal to A times S2 minus S1. Now you should notice here that when you compress the gas by an amount S1, the amount of the motion of the gas molecules on the right hand side will be smaller. So this works such that S2 is less than S1. The change in volume is negative. So this should remind you of bulk modulus. So if you look at the definition of bulk modulus, a change in pressure is equal to minus bulk modulus times delta V over V initial. And remember that this delta V has to be negative so that the bulk modulus comes out to be a positive quantity. So I see that this delta V is negative. So the change in pressure delta P is related to this change in volume minus B delta V divided by V initial. So if I substitute here, this is going to be A times delta S minus B A times delta S divided by A times delta X, the initial volume. These two will cancel. It will become minus bulk modulus delta S over delta X. And if this is a very small gas element, so that delta X is close to 0, then I obtain in this limit delta X goes to 0, delta P is going to become minus bulk modulus del S del X. So the relationship between the displacement of the gas molecules and the change in pressure on the gas are related by this equation. Delta P is equal to minus bulk modulus of the gas delta S del X, derivative of displacement with respect to X. Now remember in the description of this gas I had S of xt is S max cosine kx minus omega t. So I write the wave function S max cosine kx minus omega t. Now I have to take a derivative with respect to x. I'm going to get minus k S max sine kx minus omega t. So I can see that delta P is going to be equal to minus bulk modulus times minus k S max sine kx minus omega t, and these minus signs will cancel so that this will become bk S max sine kx minus omega t. So this part is the maximum change in pressure. Okay, so I find that the pressure description is delta P max sine kx minus omega t, where delta P max is equal to bulk modulus of the gas, the wave number k, times the maximum displacement amplitude S max. So remember, this k is 2 pi over lambda, it's the wave number, and omega angular frequency is 2 pi divided by the period. So this basically shows for us that they are out of phase by 90 degrees. One is a cosine, the other one is a sine, and they are related. The amplitudes of the two descriptions are related by maximum change in pressure is bulk modulus of the gas times wave number times the displacement amplitude. So if I look at a plot of this here, here is S as a function of x, and here is delta P as a function of x. So this is going to be, remember, um, sxt is equal to s max cosine kx minus omega t. So if I fix the time at t is equal to 0, I'm looking at this curve, and so basically this is describing t is equal to 0. I look at x is equal to 0, I have s max, because cosine 0 is 1. So the wave is coming down following the cosine curve. On the other hand, for pressure here, I have delta P as a function of x and t is equal to delta P max sine kx minus omega t. And then I'm looking at this at t is equal to 0. For t equals 0, x equals 0, I should have 0. So this starts from 0, this starts from maximum. Now the relationship between these two, remember, is the following. Delta P is equal to minus bulk modulus, the derivative of s with respect to x. Whenever the derivative of s with respect to x is negative, the change in pressure has to be positive. So I noticed that the derivative of s with respect to x in this region is going to be negative. So I look at this region here. In this region, I find that the derivative is negative. That's the slope of this. So if I take any point here, for example, this point, I take the slope at this point, I find that the slope is negative. Therefore, the change in pressure has to be positive. Now you can see that when I'm at an extremum point here, del S del X is 0, the corresponding pressure is 0. And then when I go to the next part, where I have a positive, so this is, this region is del S del X negative region. When I go to this region, that's del S del X positive region. So that will be here. This, in this pink region, I have del S del X is positive, then the corresponding pressure values will be negative. So this is delta P positive, delta P negative, etc. So I can see this relationship, delta P is equal to minus bulk modulus del S del X, looking at this behavior. So my conclusion is the following. The sound wave can be described equivalently by displacement or pressure. Alright, so the sound waves can be described equivalently by displacement or pressure. However, displacement and pressure are 90° out of phase. So why do we say that it's 90° out of phase? Because the sine function goes from its maximum to its 0 for a change in the angle delta theta is equal to pi over 2. For example, sine 0 is 1, sine pi over 2 is 0. So that's when I start from 0 here. So there's a phase difference of pi over